Good morning, students. In the last class, we discussed about the topic diffraction. So, what is diffraction and what factors the diffraction concepts that is diffraction depends on. So, what is diffraction? Diffraction is nothing but bending of the light around the edges or corners of an obstacle. So, hence the impact of the shadow region by the light. So, that phenomenon we call as diffraction, right? So, in the last class, we studied. So after that we studied on what factors. So it depends on the wavelength of light which we are going to use and the slit width, that is width between the slit. That one depends on the diffraction. So diffraction is more in sounds and less in light. So next we studied the theory by using the single slit. So considering one slit, that is AB is the slit here and screen is there. So here the plane wavefronts. So these are the plane wavefronts. When strikes the slit AB, so the points which are in this plane wavefronts acts as a sources for the secondary disturbance. So this wavefront has the number of points, so that number of points creates the, that is acts as a source for the number of secondary wavelets, that is it travels in all the direction, hence we get the diffraction pattern. In the first we studied at the, that is at the point O we get the central maximum. After that we studied the for secondary minimum, right? So diffraction patterns due to the secondary minimum in that first secondary minima and second secondary minima. The condition for the secondary minima in general form we can write theta is equals to, that is a sin theta is equals to n lambda, or it is n lambda divided by a. So where n is the order, we get n is equals to 1, 2 and so on. So this is the condition for the secondary minima. For secondary minimum, the condition is theta is equals to n lambda divided by a, that is we put the values here. N represents the order. For first order it becomes lambda by a, for the second order it becomes 2 lambda by a, and if it continuous goes on means we get n lambda divided by a. Here minima is representing what? The diffraction pattern where intensity is 0. So whenever we get the intensity 0, then we say that the pattern, that superposition of two waves is out of phase and we get the minimum values, hence the intensity is 0. So this is all about the secondary minimum. Now we are going to study the secondary maximum. Right. So in the last class we taken here the point P as secondary minimum. Now we are going to take one point Q on the screen. So this one is the point Q. So this one is the secondary maximum. Here is the central maximum. After the central maximum, we get one dark pattern, that is the dark region. That region we call as secondary minima. In that we have number of orders, that is first secondary minima, second secondary minima. Later, after the secondary minima, that is after the dark region, we get one more bright region. That region we call as secondary maxima. That is we are going to study secondary maximum. So here in the last class we taken the two waves which making the angle theta, that is diffracting angle theta. So here it is also theta, and when these wavefronts which strikes at AB, then AB becomes the wavefront. From here, the wavelets are traveling in all the direction, that is emerging in all the direction. So here we are going to find the maxima. These rays which are coming from these wavefront A and B will reach the point Q. So when it reaches the point Q, then we get the secondary maxima. Hence, we are going to study here the condition. So at what condition these rays are going to meet at Q, right? So if we write here means this becomes perpendicular drawn to the wavefront B. Then AM is the perpendicular to the wavefront B. Then BM becomes the path difference. Here the wavefront is AB. So then here angle becomes angle theta, right? So if we write for the path difference, we can write sin theta is equals to opposite, that is BM divided by the hypotenuse is AB. AB is the slit width. Then we can write A sin theta is equals to B. Yeah. Now we are going to find the first secondary maxima. Right? For first secondary maxima, what's the condition here? Taking the slit as we studied in the previous class, similar way, here we are going to take one slit, and here the rays which are emanating from AB making an angle theta with the horizontal. Next, from here, for minima condition, what we did here means, imagine this slit is divided into two equal parts in the minima case, right? So for first minima we did this slit AB into two equal parts, that is AC and CB. So here for secondary maxima we are going to find out the secondary maxima. For that we are imagining this slit is divided into three equal parts, that is this slit AB is divided into three equal parts. So here is one and here is second, C and D. So if we observe means here we get the slit AC, CD and DB. So here we get the three slits, that is AB, CD and DC. So from here also the waves are emanating and they will meet at the point where it will meet, that is it will meet at the point Q, right? So here what happens is, as similar, while finding the minimum we are considering one point in the region AC. So here we have the number of points, that is number of sources. In that source we are going to consider one source, that is from AC. For this source we get one corresponding source here, that is in CD. Then here we have one source DB, right? So here also the waves will emanating from these points. So I will call these points as C1, here it is C2 and here it is C3, right? So here these points are the points which taken in the region AC, and for that point we have corresponding one point is C2, that will be in between C and D, and we have similar way we get another one point in the region D and B, right? So here we get the point is point C3. So if we draw the perpendicular for AB, draw the perpendicular here. So this becomes BM. So this is the perpendicular, right? So if we draw the waves which emanating from these points, so from C, if I draw means it will go like this. That is C1. From C, the waves are going, that is, which are emanating like this from D, then from B, the waves which are going like this. So if we observe here, at the point C, we have half wavelength, that is, we get C, at point C, the path difference is lambda by 2. So at point C, we have the path difference, that is lambda by, here this length is lambda by 2. So at point D, we have one full wave, that is, we get that one as lambda, that is, the path length is lambda. And similarly, if we write for BM, here we observe means one full wave and one half wave, then it can be written as lambda plus 1 by 2 lambda, then we can write this one as 3 lambda by 2, right? So if we observe here, for the first one, that is for here the slit AB is divided into 3 equal parts. In the first half, that is that point C, we get the path difference is how much? That is lambda by 2. And at the second part, that is at D, we get the path difference, that is lambda. Here we get one wave. And at the finally, the path difference is B and M. Here we are getting one full wave and one half wave, that is 3 lambda by 2 can be written as one full wave, that is path difference lambda plus half lambda. Then this one can be written as 3 lambda by 2, that is the path difference between P and M is 3 lambda by 2. Next, as we say that for every points between the points AC, that is for the first half, this is for the second half CD and DB. At anywhere in the point, the path difference between these 2 points is always lambda by 2. As we already studied in the last class, that is for the minimum condition, the phase dip, that is the path difference between these 2 points is always lambda by 2. Hence, it reaches the point Q. Then what happens? C1Q, C2Q. Here the path difference is how much? That is lambda by 2. So if this one is the path difference is lambda by 2, then if we write in terms of phase difference, that is pi. Hence these two are out of phase, right? So the waves which are coming from AC and CD are out of phase. Hence these two are cancels each other. Hence we get the intensity from these two waves, that is I is equals to 0. That is the waves which emanating from AC and the waves which are coming from CD. Here the waves are in out of phase. Hence these two waves are cancels each other. Then we remaining only the waves which are emanating from D and B. That is in the last one, right? So here we get the phase difference is, that is path difference is only lambda by 2, right? So only the waves which are coming from D and B will reach the point Q. Hence we get some illusion on the screen, right? So here the waves emanating or coming from D and B, that is DB, will reach the screen, and hence some illusion on the screen will reach the screen at Q, that is at point Q. The waves which are coming from these 2 points will reach the point Q. Hence we get some wave and hence we get some intensity, that is we get intensity. So how much intensity we are getting from these two, that is from this waves, that is from the waves dB, that is 1/3 of the light. How much light is? That is 1/3 of the light. That is, the light which are coming from here, that will reach only one third of that light to the secondary minima. Only the one third of the light. Hence, the intensity is less compared to that of the central maxima. Right? So, the intensity which we are getting in the first secondary maxima is less than that of the intensity of the central minima, because here the central maxima, if intensity we are getting is 100%, then only one third of the light we are getting in the secondary maxima. So one third, that is nothing but 100 divided by 3. So here we are getting 33.3%. Only 33%. If we compare for the central maxima to the secondary maxima, that is first secondary maxima, we are getting only 33% of the light which falls onto the secondary maxima, that are which coming from the wavefronts that are coming from D and B. So understand this one. Here we have three phases, that is AC, DC, AC, CD and DB. The waves which are coming from AC, CD and DB. So here in these two, the phase difference is pi by 2. Hence, the intensity from this we are getting I is equals to 0. The only waves which reach the point is that are coming from D and B. That is, the waves which are reaching is one third of the actual light, that is one third of the incident light. Hence, its intensity is less. Hence, we get the maxima. If it is intensity is falling on the screen, means if we are getting the intensity nothing but we are getting the maxima. For that condition, we have to write. For that case, when we are getting the intensity, when the path difference is 3 by 2, then only we are getting the intensity. Then we can write A sin theta is equals to, here Bm value is how much? That is 3 lambda divided by 2. Right? So this is for the first secondary maxima. For first secondary maxima, A sin theta is equals to 3 lambda divided by 2. That is the waves only coming from D and B. Right? Similarly, if you find for the secondary maxima, for second secondary maxima, considering say the slit A, B, now it will reach after Q, we get 1 if it is first secondary minima. So this one is the first secondary maxima. Then here we get 1 point, that point is the, so here we can take that point as P dash. This one is it is the first secondary minimum. Here we get the secondary minima. In the last class we discussed first secondary minima and second secondary minima. Now we are going, here we get the first secondary maxima. After the second secondary minima, here we have 1 point, that will secondary maxima. So now these two waves which are coming from A and B will reach the point, that is, it will reach the point Q dash. Then only we get the second secondary maxima. Now here what we are going to do is, this wavefront, that is AB is the wavefront. This wavefront is divided into 5 equal parts. 1, 2, 3, 4, and this one is the 5. So 1, 2, 3. So here C, D, E, F, right? So like this, in the last, for secondary minima, we divided the slit into 4 equal parts. For next secondary maximum, we are dividing the wavefront AB into 5 equal parts. So this one is, so all these races are meeting at the point Q, right? So now same, draw the perpendicular, this becomes M. Next, considering the points, that here is the point between A and C. For the similar point, we are getting corresponding point, that is in between C and D, and if we consider one point between D and E, then for that we have a corresponding point between E and F, and if we consider the one point F and B. Right now, the waves which are coming, the points, the difference between these 2 points is the path difference is pi by 2. Between these two is the path difference is pi by 2. So now, if we draw the waves which are coming from these parts, so now observe here at the point C, we have the path difference is lambda by 2. At point D, the wave is full wave, that is the path difference is lambda. So here we are getting the path difference lambda by 2. At the point D, we have the lambda, and point E, we have 3 lambda by 2, and at point F we have 2 lambda, and at point B we have here 2 waves plus 1 half wave, 2 lambda plus lambda by 2, that is 5 lambda by 2. So this 5 lambda here, if we observe the points, means we get the 5 lambda by 2. For any points between these two, then the path difference is lambda by 2. Now if we consider the points, so if I consider this point as C1, C2, here it is E1, E2, and here it is F1. So these are the points which we are considered in between the parts, that is AC, DE, EF and FB. Now if we observe this, the path difference between C1 and C2 is lambda by 2. So similarly, if we take the path difference between E1 and E2, that is also lambda by 2, and also for F1 it is lambda by 2, that is minus 0, then we get the lambda by 2. So now if we write the path difference for C1 Q dash to C2 Q dash, then the path difference is lambda by 2. So if we write similar by E1 Q dash to the difference of E2 Q dash, then the path difference is lambda by 2. So only remaining we are getting the wavefronts which are coming from F and B. From FB reach the screen at Q dash. So if we observe here, the only the rays which are coming from FP will reach the screen at Q dash. So here the phase difference is pi, that is 180 degree. Hence here it is out of phase. Then here we get the intensity I is equals to 0. So here also the phase difference is 180 degree and it's out of phase, and its intensity is also 0. Now the waves which are coming from only FB, from here the waves which are coming will reach the point Q, then if you observe here, the light will be illuminated or illusion on the screen only the 1/5 of the incident light. 1/5 of the incident wavefront, that is AB. So in first secondary maxima, we are getting only 1/3 of the incident wavefront. In the secondary maxima, we are getting only one fifth of the incident wavefront. That's why the intensity decreases as the order increases. So here also we getting the intensity, but it compared to the intensity which we are getting is very less compared to that of the central maxima. So if we are 100% here, that is at the central maxima we are 100%, then the wavefronts which reach on the Q dash, that is at the secondary minima, that is only 20%. Hence, from this we can conclude that the intensity decreases as order increases. Intensity decreases as order increases. That is nothing but the order, nothing but first, second, third. As we goes on, then its intensity goes on decreasing, right? Hence, if we write the condition for the secondary maxima, that is A sin theta is equals to Bm. So Bm value is 5 lambda by 2, right? So here we get the intensity. Hence, that one we call as the secondary maxima. So this is about the secondary maxima. In the last class we discussed about the secondary minima. Here we are getting the secondary maxima, but intensity is less compared to that of the central maxima, right? Because here the waves which are coming from these parts are out of phase, hence these are cancelled out. Hence we get the intensity 0. Only the intensity which we are getting from the waves which are coming from the phase, that is FB. From here, the waves which are coming will reach the point Q, only 1/5 of the incident wavefront. Hence, the intensity at Q dash is less compared to that of the central maximum. So, if we write the general form of the secondary maximum, if we write for secondary maxima, in general form, we can write A sin theta, that is equals to, here if you observe means it is 3 by 2 lambda, here it is 5 by 2 lambda. If it goes on, next one is 7 lambda by 2. So 3 lambda by 2 can be written as lambda plus 1 by 2 lambda. Here 5 lambda by can be written as 2 lambda plus 1 by 2 lambda. So if we write for the nth value, then we can write this one as n lambda plus 1 by 2 lambda, right? This one can written, if 5 lambda by 2 can written as 2 lambda plus 1 by 2 lambda. If we take LCM, then we get the 5 lambda by 2. 3 lambda by 2 can written as lambda plus 1 by 2 lambda. If we take LCM and simplify means we get same value, that is 3 lambda by 2. If we write for the nth value, that is for nth order, either it may be 7th order, 8th order, then we can write as, here if you observe means here it is 1, next here it is 2, for third order it becomes 3 lambda plus 1 by 2 lambda, for fourth order it becomes 4 lambda plus 1 by 2 lambda. If we write similar ways, we can directly write n lambda plus 1 by 2 lambda, that is n lambda plus 1 by 2 lambda. Here we take lambda as common, then we can write n plus 1 by 2 into lambda. Here we are considering this angle is very small, hence we write A theta is equals to n plus 1 by 2 into lambda, then theta is equals to n plus 1 by 2 into lambda by a. This is the condition for the secondary maximum. If we substitute n value 1, then we get first secondary maxima. If we substitute n value 2, then we get second secondary maxima. If we substitute n value 3, then we get third secondary maxima. So hence n value varies from 1, 2 and so on. Right? So this is about the secondary maximum. So understand this one. So at the center we get the maximum intensity. Then for the first secondary minima we get the dark region, again bright, again dark and again bright. So wherever we get the bright pattern, that is bright region, here the intensity goes on decreasing. In the interference pattern, all the bands on the intensity, that is on the fringes, all the intensities are constant, that is they have the same values, but here the intensity goes on decreasing, right? So if we draw the intensity distribution curve, so if you write for the conditions here, that is secondary minimum, that is theta is equals to n lambda divided by a. Secondary maxima, theta is equals to n plus 1 by 2 into lambda by a. So in these two cases, n values varies from 1, 2 and so on. So now if we draw the intensity distribution curve for this one, so here we are getting the maximum intensity. So this is, I will take intensity I. So from here, so if we draw the intensity distribution curve, so here I am taking along horizontal, we have the intensity. So here we are getting the intensity is maximum here, that is at the center, at this region we getting the intensity is maximum. That's one we call as this one as central maximum, right? So after the bright fringe, so at this central maximum we have intensity is maximum, right? So after here we are getting the intensity maximum, nothing but this one is the bright fringe, that is bright region. After that we are getting here is the secondary minimum. So this one is at the first point, hence this point is first secondary minimum. So this is the first secondary minima, and here is we getting first secondary maximum. Next, here we are getting the intensity is less, that is we are getting the dark region, hence this point is second secondary minimum. And here we are getting the maximum, and this point we have taken as second secondary maximum, right? So this is the point P, that is for the secondary minimum, and this is the point Q, that is for secondary maximum. As we explained in the previous, that is P is the secondary minimum and Q is the secondary maximum, and here O is at the central maximum, right? So if you observe here, here is the maximum intensity, then for the first secondary maximum, the intensity reduces. So if you observe here, the intensity is reduces, and if you observe here for the next secondary maximum, intensity is goes on decreasing as the order increases. Right? So this is about the intensity pattern. So this one is the intensity. So if we write along the horizontal, so this one is intensity, and here it is part difference. Then if we draw the curve, it is symmetric. So if we draw above one side, then similar we get in the denominator, that is in the bottom side of the pattern, right? So here we get the intensity is maximum. When the intensity is maximum means the point O is at the same distance from these wavefronts, that is from A and B, O is at the same distance, that is AO is equals to BO, then no path difference, then only we get the maximum intensity. And next we get the maximum, all the intensities we are calling maximas. Then here the intensity is less compared to that of the bright fringe, that is the intensity maximum. Here we get only 1/3, and here we get 1/5, and here we get 1/7. As it goes on, then we get 0, right? So this is the intensity distribution curve. So we are not getting constant bright regions and constant dark regions. As the order increases, as the order goes on increasing, then we are getting the different intensities, 1/3, 1/5 and 1/7, that of the maximum intensities, right? So this is about the diffraction, the wavefronts which are coming and incident on a single slit. Here we are considering the slit as single slit. Then each point in these wavefronts acts as a source for the secondary waves. From here, the points acts as a source, and the waves which are emanating in all the directions according to Huygens principle. So out of those rays we are considering few rays, and by using those rays we constructed the intensity pattern. That is, we are getting the secondary minimas and secondary maximas. The condition for secondary minima is theta is equals to n lambda by a, and for secondary maxima the theta is equals to n plus 1 by 2 into lambda by a. Right? And also here in the intensity distribution curve, the intensity goes on decreasing. First is the bright region, at the center only we get the bright region, afterwards we get the dark region. Wherever here the intensity at the bottom, it represents I is equals to 0, that is I is equals to 0 represents what? That is the dark region. And here we have the intensity for the second maximum, and here also for the secondary maximum, here also for the secondary maximum, but here the intensity goes on decreasing. So intensity goes on decreasing, hence we are getting central bright band. After that the illusions, that is lights, are very less intensities, right? So this is about the diffraction by using the single slit. Next, the difference between interference and diffraction. So few times they asked the question, write the difference or note the difference between the interference and diffraction for 3 marks. Interference and diffraction. So first point is we have to write the definition of the interference and we have to definition of the diffraction. So here in the interference, distribution of the light, when two light waves are superimposed, then we get the interference. Here in diffraction, that is the bending of the light around the obstacles or around the edges or corners of an obstacle, then the light impact of the shadow region, that is by due to the light, that is the phenomenon we call as diffraction. So next point, if we write, means intensity. So in interference, the intensity of all the regions, that is dark region and the bright region, all are of the same width, and also the intensities are constant for bright fringe. The intensity for bright fringe remains constant, right? So if you write this one as the second point, that points on intensity. So intensity of the bright fringe remains constant. Here the diffraction bands are in diffraction bands, that is for the bright bands intensity decreases. Intensity decreases as order increases. Here the diffraction bands intensity, that is for the bright bands. Here also we are discussing bright band. In both the cases, the dark bands we getting the intensity is 0. That is the dark region we have always the intensity is 0. Here we are discussing only the bright bands, that is bright fringes remains constant. At all the fringes the intensity remains constant, and here in diffraction bands the intensity decreases as order decreases. If goes on, the order goes on increasing, then diffraction decreases. That is diffraction bands decreases. That is intensity decreases. Next, here bandwidth or fringe width. Bandwidth is constant. So each band have the constant bands. Here the band, that is the diffraction bands are goes on decreasing. So if you observe here, so we get the maximum band, that is the width is this much, and if you observe here the band of the secondary maxima is less, and for secondary maxima it goes on decreasing. So here also the bandwidth decreases or diffraction bands bandwidth decreases, right? So next, if we write for the condition for maximum intensities, either we can write only in path difference or in phase difference, that is for the maximum intensities in terms of path difference. In case of interference, the path difference is equals to n lambda. So in case of phase difference, we can write the value of the lambda in terms of phase is 2 pi, then we can write 2n pi, right? So here the lambda value is 2 pi, then if we write in case of phase difference, then we can write 2n pi. So here condition for maximum intensities, that is secondary maximas, then path difference is equals to n plus 1 by 2 into lambda by a. So this is for the maximum intensities in case of the diffraction, that is phase path difference is equals to n plus 1 by 2 into lambda by a. So similarly, if we write for phase difference, we can write n plus 1 by 2. In case of lambda, we can write 2 pi by a. So just we replacing the lambda value in terms of phase, that is 2 pi. So on the last, we can write the intensity distribution curve in case of interference and diffraction. So this one is the interference, intensity along y-axis and path difference along x-axis. Then we get so if you observe here, so intensities all are constant, that is constant intensities. So similarly, if we write here, so intensity along y-axis and path difference along x-axis, then intensities goes on decreasing. So for the examination, if they ask for the 3 marks, then we can write only the 3 points. So first point, second, third, and here it is fourth, and one more point is the definition. So here and here, if we write the definition, then we get the 5 points. So several times they ask for 3 marks, right? So the theory of the diffraction is very rare. They ask only if they ask for the condition for the maximum intensities, that is in terms of path difference, right? For the secondary maximas and secondary minimas. So this one is the important, the difference between interference and diffraction. So here the intensity remains constant, its intensity goes on decreasing. Here the bandwidth remains constant, here bandwidth decreases. Next, condition for the maximum intensity, that is n lambda, here it is 2n pi in terms of path difference and phase difference. Here condition for maximum intensity is n plus 1 by 2 lambda by a, and here it is n plus 1 by 2 pi by a. And finally we can write the intensity distribution curve, I intensity versus path difference. Here if you observe means all the curves are at the same height. Here the curves are goes on decreasing. So this year, that is 2020 March, they written the exam, they asked for the derivation for bandwidth, that is beta, for 5 marks. So this one is very important derivation. If they ask the derivation, that is to find the fringe width or bandwidth derivation, or they may ask the problem on this topic. So for 5 marks, this one is very important, and for the 3 marks, this one is important, right? So in the diffraction, we have the difference between interference and diffraction, and also the theory of diffraction. So this is about the diffraction. right? So in the next class we will discuss about the resolving power of the microscope and telescope.